NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we solve simple logarithmic inequalities when the base a is greater than 1. Example, solve the two general forms, log base a of n greater than 0 and log base a of n less than 0, where is greater than 1. Let's lay out the two cases side by side and unfold the steps exactly in the algorithmic order shown. On the left, we handle log base a of n greater than 0. On the right, we handle log base a of n less than 0. Remember throughout that it is greater than 1. So the exponential function a to the x is increasing and inequalities keep their direction. Case 1 follows 3 simple lines. First, write the inequality exactly. Log base a of n greater than 0. Next, convert to exponential form. Because it is greater than 1, the inequality direction stays the same, giving n greater than a to the 0. Finally, use the zero exponent property a to the 0 equals 1, so n is greater than 1. Now case 2, again in the same 3-line structure. First, write the inequality. Log base a of n less than 0. Convert to the exponential form. Since it is greater than 1, the inequality direction remains, n less than a to the 0. Finally, simplify a to the 0 equals 1, and also include the logarithm domain n greater than 0, giving 0 less than n less than 1. Summary. For base a greater than 1, converting from log to exponential keeps the inequality direction. The two canonical outcomes are n greater than 1 and 0 less than n less than 1. In this lesson, we will learn how to solve logarithmic inequalities when the base a is greater than 1. We will follow 4 cases exactly, and we will visualize each result on a number line. First, always remember the domain of a logarithm. The argument n must be strictly positive. We will use that in 2 of the 4 cases. Case 1. Start with log base a of n is greater than 1. Convert to exponential form. N is greater than a to the power of 1. Simplify the exponent. N is greater than a. Now, we will show this on a number line. Case 2. Start with log base a of n is less than 1. Convert to exponential form. N is less than a to the power of 1. Now apply the domain n greater than 0. Therefore, 0 is less than n and n is less than a. Case 3. Start with log base a of n is greater than negative 1. Convert to exponential form. N is greater than a to the power of negative 1. A negative exponent gives 1 over a. Therefore, n is greater than 1 over a. Case 4. Start with log base a of n is less than negative 1. Convert to exponential form. N is less than a to the power of negative 1, which is 1 over a. Apply the domain n greater than 0. Therefore, 0 is less than n and n is less than 1 over a. To summarize, for base a greater than 1, convert the logarithmic inequality to exponential form and include the domain n greater than 0 when the result bounds n above 0. The 4 results are exactly as shown on the screen. We will reconstruct the exact step-by-step solution for 2 logarithmic inequalities, matching the structure shown in the provided image. Example. First inequality. Apply the base 10 logarithm inequality rule for a greater than 1. We rewrite the inequality in exponential form and include the base information. Then apply the domain condition of the logarithm to build a double inequality. Add 3 to all parts. Divide by 2. State the solution set in interval notation. Now, the second inequality from the image. Second inequality. Use the same inequality rule with base 7 greater than 1. Next, apply the domain requirement to form a strict compound inequality. Rewrite it as a system, 1 inequality for positivity and 1 for being less than 1. Solve that system to obtain the x region shown in the image. Finally, state the interval solution. Summary. Interval solution. Summary. For base greater than 1, the inequality log of f of x less than c means 0 is less than f of x less than a to the c. Example. The problem is log of open parenthesis x squared minus 2x minus 3 close parenthesis is greater than or equal to 0. Step 1. Convert the logarithmic inequality to exponential form using base 10. The rule says log base b of y greater than or equal to c implies y is greater than or equal to b to the c, provided b is greater than 1. Applying this with base 10 gives x squared minus 2x minus 3 is greater than or equal to 10 to the 0. Step 2. Simplify the right-hand side. Any non-zero number to the 0 power equals 1. Thus we have x squared minus 2x minus 3 is greater than or equal to 1. Step 3. Rearrange to a standard quadratic inequality. From a greater than or equal to b, we get a minus b greater than or equal to 0. Therefore, x squared minus 2x minus 4 is greater than or equal to 0. Step 4. Solve the quadratic inequality. Use the quadratic formula to find the zeros of x squared minus 2x minus 4 equals 0. The roots are 1 minus square root of 5 and 1 plus square root of 5. Since the leading coefficient is positive, the parabola opens upward, so the expression is non-negative outside the roots. Hence, x is less than or equal to 1 minus square root of 5, or x is greater than or equal to 1 plus square root of 5. Step 5. State the solution set in interval notation. If x is less than or equal to a or greater than or equal to b, the set is the union of the intervals from negative infinity to a, closed at a, and from b to positive infinity, closed at b. Therefore, d equals open parenthesis negative infinity, 1 minus square root of 5 close bracket union open bracket, 1 plus square root of 5, infinity close parenthesis. Recap. We converted the log inequality to an exponential inequality, simplified, moved everything to one side, solved the quadratic using the quadratic formula, reasoned about the sign of the upward opening parabola, and finally wrote the solution set in interval notation. The problem is the fraction open parenthesis log base 10 of x close parenthesis squared minus 3 times log x plus 3 over log x minus 1 is less than 1. Step 1. Move everything to the left by subtracting 1, so we can compare the expression to 0. Step 2. Put this over a common denominator, log x minus 1. Now, simplify the numerator. Notice it becomes a perfect square. Open parenthesis log x minus 2, close parenthesis squared. Step 3. A square is never negative, so the numerator, open parenthesis log x minus 2, close parenthesis squared, is greater than or equal to 0, and it equals 0 only when log x equals 2. For the whole fraction to be strictly less than 0, the numerator must be positive and the denominator must be negative. That gives two conditions. Log x minus 1 is less than 0 and log x is not equal to 2. To see the sign clearly, let t equal log base 10 of x. The denominator is negative when t is less than 1, and the numerator is 0 only at t equals 2, which we must exclude. Step 4. From the condition, log x minus 1 is less than 0, we get log x is less than 1. Step 5. Convert the logarithmic inequality to an exponential 1. Because the base 10 is greater than 1, the direction of the inequality does not change. So x is less than 10 to the power 1, that is 10. Also, the domain of the logarithm requires x to be positive. Together we have 0 less than x less than 10. Let's picture the final answer on the x number line. It is the open interval from 0 to 10, not including the endpoints. Example. In this problem we will find for which values of the quadratic equation x squared minus 2 times the quantity 1 plus log base 10 of a times x plus 1 minus log squared of a equals 0 has two roots with different signs. Step 1. A quadratic ax squared plus bx plus c equals 0 has roots with different signs, exactly when c divided by a is less than 0. For our equation, a equals 1, b equals negative 2 times 1 plus log base 10 of a, and c equals 1 minus log squared of a. So the condition becomes the fraction 1 minus log squared of a over 1 is less than 0. Step 2. Dividing by 1 changes nothing, so we get 1 minus log squared of a is less than 0. Step 3. Move the term to the other side. This gives log squared of a greater than 1. Step 4. Take square roots of both sides, and remember that the square root of a square is the absolute value. So the absolute value of log base 10 of a is greater than 1. Step 5. Split the absolute value inequality into two cases. Either log base 10 of a is greater than 1, or log base 10 of a is less than negative 1. Step 6. Converting from logarithms to base 10 exponents. Log base 10 of a greater than 1 means a greater than 10. And log base 10 of a less than negative 1 means is between 0 and 10 to the minus 1. That is between 0 and 1/10. Step 7. Combine the two cases. The parameter a must lie in the union of the intervals from 0 to 1/10 and from 10 to infinity. Let's also picture this on a number line. Step 1. Establish the ranges of the base and the exponent. Because 3 is bigger than 2, the quantity log base 3 of 2 lies strictly between 0 and 1. And since sine of alpha always lives between negative 1 and 1, we have this pair of inequalities. Step 2. Visualize how the power function behaves when the base is between 0 and 1. The graph of b to the x is decreasing for such a base b. Therefore, to maximize b to the x, we should minimize the exponent x. For our expression, the exponent is sine of alpha, so its minimum is negative 1. Step 3. Write the maximization statement and plug in the minimum possible exponent. Step 4. Apply the negative exponent rule. A to the power negative 1 equals 1 over a. Step 5. Use the reciprocal property of logarithms. 1 over log base b of a equals 1 over log base b of a equals log base a of b. This yields the final answer. Therefore, the maximum value of open parenthesis log base 3 of 2 close parenthesis raised to the sine of alpha is log base 2 of 3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.